So in Lab 5, we're going to play with a common emitter amplifier. And what a common emitter amplifier is here's an example of one. And it's a middle-of-the-road voltage amplifier. It has pretty good voltage gain from V in to V out. It has very good input resistance looking in from the input, so it doesn't load the thing that it's connected to. And it's got okay output resistance, so it's got when it has a load, you don't lose much voltage off of VO to drive that load. So it's a decent middle-of-the-road amplifier. You'll be studying it in class, and it's an AC amplifier. And these two capacitors here on the input and the output actually decouple any DC that's present at the input from DC that's going on inside the amplifier from DC at the output. So these are chosen to be essentially a short circuit at the frequency of interest and an open circuit at DC. So they're a coupling capacitor, just like when you use an AC coupling capacitor on your scope. It does the same thing. So since this is lowercase, we assume that VI has no DC associated with it. And if it did have any, we wouldn't care, because we're going to get rid of it using CI. So CI and CO are coupling capacitors is what we call them, and they're used to just disengage the DC that's present at VC here, for example, from the DC at the output. We do need a RB here, even though it doesn't do a whole lot. It enforces a zero or close to zero voltage at the base of the transistor. If we didn't have a resistor here, because we have this capacitor here, it would be decoupled and the base would be floating. And then our BJT might not be biased properly. So generally speaking, you'll derive, in the handout we derive the equations that support this, but generally speaking, the AC gain from V in to V out is the collector resistor divided by the emitter resistor. And interestingly, this is largely independent of the value of beta, which is very good because as in Lab 4, you saw beta is very uncertain and changes a lot. So what does CB do for us here? Well, this is your first example of a circuit that acts very different at DC than it does AC. And CB is part of the reason for that. At AC, this thing short circuits, and the amplifier only sees RE1. At DC, on the other hand, you see RE1 and RE2 both. So that allows you to have a different gain for the DC than for the AC. So why do we have any RE here? So if we're just looking at the AC gain, it's RC over RE. Whoops, it's RC over RE. So we can actually look at the small signal model where we've replaced all of the power supplies by zero because this is 0 volts AC, 0 volts AC. All of the capacitors are wires now, and then we have the small t model here. So if we're looking, we have RC over RE1. It turns out to be the voltage gain. So why not make RE1 just really, really tiny? And the answer is over here in the DC model. So in the DC model, it shows we need to make sure that our BJT is in the active mode. So we need to make sure that there's a good VCE when we add the DC VCE plus the AC VCE. So when we put them together, we still want to have it in the active mode because all of these models break down as soon as this BJT leaves the active mode. So we want to make sure that that's in there. So we ask you to do some predictions and some computations on this based on several different beta values. In a separate video, I explained how to use something like ease to automate that circuit analysis. So there are a fair number of equations here, and we're asking you to do them for 3 or 4 different beta values. It might be worth looking into ease and learning a little bit about that to help you with your circuit analysis. So that's a separate video. I encourage you, before you do the pre-lab, to go look at that. And if you do that for the pre-lab, make sure you turn in screenshots of your ease stuff as documentation. Don't just give me answers and say, yeah, we did it in ease. That's not quite enough. Okay, so turning our attention to the specific circuit now that we have, let's see what it looks like when we simulate it. So we're going to start out with a 400 millivolt input. This thing has a gain of 15 volts per volt. Let's make this thing a little bit bigger. So here's what a couple cycles of the input looks like. There we go. So let's get rid of Vs, and you can see that Vin here is 400 millivolts and Vout is about 2.5 volts. So it's an inverting amplifier, and as Vin goes up, Vout goes down. And we can look at Vc and Ve separately, but what's the most interesting, and this is one of the reasons it's really handy in simulation, is we can actually directly plot IC and VCE. And this allows us to go and check, for example, when we're looking at how much can we turn it up before it stops working properly. We can look at IC and make sure it's not cut off. We can look at VCE and make sure it's not saturated. So just plotting IC and VCE there allows that to happen very easily. Okay, so that's the basic setup for this lab. You're going to put a sine wave in, you're going to get a bigger sine wave out. So let's take a look at the actual procedure then. I think I already mentioned all this. The pre-lab, first you're going to take the generic R's that we do in the handout, and you're going to find R's that achieve this operating point. And you're going to specify those R's with both the ohmic value and the power specs. Well, in order to specify a 1/4 watt resistor, then you need to compute the expected power dissipation for it and make sure that it's below a 1/4 watt. So you can't just say, I need a 1/4 watt. You need to actually go and make sure that you do, because as you know by now, I give you things that don't fit in a 1/4 watt sometimes. So you need to go check your power before you specify your power. But every resistor going forward needs two numbers, a power and an ohmic. Then in the pre-lab, we ask you to predict these 6 quantities using the equations in the handout for these 3 betas. Again, I encourage you to use ease or something like that, or MATLAB at least, to do that computation and turn in the source from that as well, not just the answers. And then in your lab notebook, make a data table to make sure that as you're going through this lab, you record all the data. So it's easy to miss something as you're in lab. Then in lab, what are we going to do? Well, we're going to do the same kind of thing. We're going to build this thing, and we're going to do all the DC measurements. We'll put a very large load resistor on there so that it doesn't really affect it. And we'll measure VB, VC, and VE, make sure it's in the active mode in DC with no signal going through it. Then we will put a small signal going through it. We'll monitor it with the oscilloscope and make sure it's a sine wave going in, sine wave going out. Then we'll measure R in and R out. So let's look at those measurements. So AV, best practice is to, like I said, monitor it with the scope, make sure that they're clean sine waves. Then you measure RMS with the DMM. So that's going to be a more precise measurement. So measure the input voltage, the output voltage, divide the two, you get your voltage gain. Rin and Rout requires a little more explanation. Rin, remember, is a Thevenin equivalent resistance looking from the input. So if I know in here I have a fake Rin or a theoretical Rin, and I want to see what that value is, I can't just put a DMM there because Thevenin equivalents don't work that way. The DMM injects some current, some DC current into it, and this is an AC amplifier. So what I need to do is pass a sine wave through it, and I'll pass the sine wave through it, and I'll monitor it, and then I'll adjust our pot set up as a variable gain resistor. So the resistance between pin 2 and pin 1 changes. And I'll adjust our pot until VI is half the sine wave of VS. And when that's the case, I know that R pot is equal to Rin, And then I can take our pot out and measure it with my DMM and get an actual number for that. One of the reasons we do these predictions here, we're going to predict what our in will be. Sorry, we're going to predict what our in will be so that we know what size pot to use in the experimentation. Similarly, our out we've predicted. So we're going to remove the really big 1 mega ohm resistor, and we're going to put the 1 mega ohm resistor in there. We're going to measure the output sine wave. Then we're going to remove the really big one in there, and we're going to put a pot in there. We're going to tweak the pot until this output is half what it was before. When that's the case, then you know that you're splitting this amplified voltage between your R out and R pot. And so again, you can remove R pot from your circuit, measure it with your DMM, and you have a measurement for RO, which you then compare against your predictions from the circuit lab. Do make sure when you're adjusting R pot, you're changing how much current this thing takes. Therefore, it's possible you're changing how much current the amplifier takes from your signal generator. And since the signal generator has some series resistance, you may be changing VI a little bit. You shouldn't much, but you should check it. So make sure that your VI is the same when you have the big 1 mega ohm resistor here as when you have the pot. So you may have to go back and tweak your signal generator just to make sure that that's the case. Then the last step, all this is linear operation. The last thing we ask is you turn it up until it starts to clip. And what we mean by clip is it's no longer a sine wave. Something is causing your transistor to leave the active region for just a brief moment in time. So let me show you what that looks like. So let's maybe go up to 475 millivolts and run a simulation. Yes. So my output now, you can see, is just clipping a little bit on one end. This end still looks pretty good. It's still a sine wave. So the question that we're going to ask you is why? Where is it clipping and why? Well, it's clipping at the bottom. That doesn't really tell me anything. There's two ways I can leave the active mode. One is by cutoff, and one is by saturation. So in the simulation, it's easy. I just plot IC and VCE. Well, IC you can see at the flat spot, which here's where we're investigating. At the flat spot, IC is quite high, 3.8 milliamps. VCE, on the other hand, is quite low, 41 millivolts. And we know that in theory, if it's less than 0.2 volts, you're in danger of saturation. So this particular one is saturating first. You can see it's getting quite close to cutoff. And if you turn it up just a little bit more, you'll see it cut off. So if we go to 500 millivolts, you can see it's cutting off here and saturating over here. But in lab, what do? Because we can't plot IC. We can use the math mode. We can plot VC. We can monitor VC and VE with the scope and then use the math function to show VC minus VE. So that's not the problem. We can go ahead and generate this and check when it's flat, is VCE low? And in this case, it'll say yes. But what if it was cut off? And for different ones of your transistors, it may be cut off, it may be saturated. We don't know. So how do we check IC? Well, we can't check it directly, but what we can do is we can get it indirectly. So we know that IC here is equal to 9 minus VC divided by RC. Well, we can monitor all that with the scope. So we can go ahead and let's add an expression for that. If we have 9 volts on one channel, we can just put the channel 1 on the 9 volt power. We can put VC on the other power. And if I want to make the scale work here, I can divide by RC. Now, since you're checking this against 0, dividing by RC doesn't do anything. So let's leave that off and let's go to advanced graphing and bring that down. I'm going to bring that down to its own set of axes there. Okay, so now you can see here IC is up here and 9 minus VC is here. So whenever IC is 0, this thing is going to be 0. So on the scope, that's how we're going to monitor VC IC to check for the cutoff condition. So in the third step, that's what we're asking you to do, is to turn it up and tell where does it clip first. And you want it to clip just a little bit. So you want just a little section of clip here. What you'll find is if you keep turning it up, it'll do this and then it'll start going wonky, because when you really get well beyond the limits of active, a lot of our models really break down. So when you want to see it clip, you want to see it just barely clip, not go completely off the edge. So